Welcome back to A Slice of Physics. As we get ready to wrap up the content for Physics 1, the last topic we turn to is oscillations. Oscillations are back and forth motions that you are familiar with, like for example a pendulum going back and forth, or if you have a mass on a spring, which is the example we're going to start with. We'll study how that oscillates back and forth on a spring. And then there are certain specific kinds of oscillations that are described by sinusoidal curves. And you guys know sinusoidal curves are either sine or cosine curves. And so that's where we're going to start our discussion. A mass on a spring, a pendulum, a wave, which a lot of physicists and astronomers spend a lot of time studying because light is an electromagnetic wave. Those are all examples of simple harmonic motions. So we're going to be studying that. We'll talk about what is the force that's needed to create a simple harmonic motion. We will look at the specific example of a mass on a spring to see how it oscillates and how we study it. And then we'll discuss some terms like amplitude, frequency, and period for a simple harmonic motion. All right, so let's take the example of a spring. So I'm going to take, in this case, a horizontal spring. And if I leave the spring alone, that's where it wants to sit. So that's its equilibrium position. So let me mark that over here. This is its equilibrium point. Okay. And then I connect a mass to it. And I put that mass on a frictionless horizontal track. So this track is horizontal, it's frictionless. And so that's an ideal world situation we're taking. And so the mass is happy sitting there and it's in equilibrium when it's over there. But what happens if I stretch it? If I pull it to the right and I stretch the spring by a certain amount and the mass is now over here, you guys know from previous discussions that a spring that is stretched wants to pull back. So the spring is going to apply a force on the mass that's to the left in response to the spring being stretched to the right. So this delta x is displacement from the equilibrium position of the spring, and that results in a force of the spring that is a restoring force, so it wants to go back to the way it was. And if I compress the mass and push the spring in, now I have a displacement from the equilibrium position to the left. So now I got delta x that way. And now you know that if I compress a spring, the spring wants to push back and get back to its original equilibrium position. So either way, you notice that the spring and the displacement are opposite in direction. And you studied before that the spring constant, the restoring force of a spring was minus k times delta x, where delta x was the displacement from the equilibrium position and k was the spring constant, which has to do with how stiff the spring is. And the minus simply reminds us that this force is a vector, the displacement is a vector, and the minus tells us that the restoring force of the spring and delta x are always opposite in direction. K is a positive number, so when you take a vector, multiply it by a positive number, and then multiply it by a negative sign, you end up with the opposite direction. So in studying the motion of this mass on a spring, if you stretch it and let it go, it's going to be going back and forth in this fashion. It's going to first go to the left, and when you release it, you're going to release it at rest. So the spring will pull it in, and as it's pulling in, it's going to speed up. So from here to here, it's going to speed up. When it gets to the equilibrium point, it's going to be the fastest. There is no force on the mass at that time in the horizontal direction, but because of inertia, it'll push forward and it'll move into the spring, and then the spring starts pushing it back. So it'll slow down as it goes here, come to a complete stop momentarily at the end, and then turn back around and speed up, and then slow down and keep going back and forth. You're familiar with this as in the motion of a pendulum, etc. So in studying this motion, let's note that the restoring force, the force relationship to the displacement, is a linear relationship. So what we mean by linear relationship is it's a power of 1. It's not related to the square of the displacement or the cube. It's related to just the displacement. And when you have a restoring force that has a linear displacement, it results in a simple harmonic motion. A simple harmonic motion is an oscillating back and forth motion that can be described as a sinusoidal function, which means like either a sine function or a cosine function. So let's look at what that looks like. Oh, by the way, before we even do that, let me just tell you that there are a couple of key terms here. So there is period of an oscillation, that's capital T. And the period of the oscillation is similar to the period of circular motion. It's the time it takes for one full oscillation. So in the circular motion, it was the time it took for one full rotation or revolution. In this case, it's the time it takes for one full oscillation. So what is a full oscillation? If I start at the rightmost end, I go all the way to the left, and then I turn around and come all the way back to the right. That is one oscillation. So one full complete cycle, and then it starts repeating itself. So the period that's written as capital T is the time for one full oscillation. It's measured in seconds. A related term is frequency, which is written as lowercase f, and that is the number of oscillations per unit time. So in this case, let's say per second. Let's stick to SI units for now. So that'll give me a unit of hertz for frequency. It could be oscillations per minute, which would be RPM and so on, or oscillations per minute in this case. And you guys know from circular motion, it's still true that frequency and time are inversely, but period are inversely related to each other. So F is 1 over T, T is 1 over F. Okay, so you can count on those relationships. And then the last thing we have is something called the amplitude of oscillation. The amplitude is the maximum displacement from the equilibrium position. So in this case, this would be plus A. So this end point, the displacement at the end point is the amplitude. And if I've got the equilibrium position in the middle, displacement to the right is positive. So when I'm at the very end here, my displacement is plus A. When I'm at the very left, my displacement is minus A. So A is the amplitude of oscillation. Amplitude, capital A, amplitude, only one E. Capital A is the maximum displacement from equilibrium. And it'll be measured in SI units in meters. So with these basic terms down, period, frequency, and amplitude, let's take a look at what a position time graph of that mass on a spring oscillating looks like. So I've got, once again here, the spring in its equilibrium position here, stretched to one end over here, and then when it compresses, it's stretched to this point here. So I've got my equilibrium here, plus A over here and minus A over here, right? The maximum displacement on either side. Equilibrium would be zero displacement. So what I want to plot is the position time graph. So here we go back to something that we started very early in the semester. So I've got position on the x-axis, on the y-axis. So this is position in meters, let's say. And then I've got time in seconds on the x-axis. Time is the independent variable, so it's plotted on the x-axis. Position is the dependent variable, so it's plotted on the y-axis. At time 0, let me set this as time 0. So my displacement or position at time 0 is plus A, right? Because that's where I stretch the spring to and let go. And then when I let go, this block is going to start moving to the left. So it's going to come closer to the origin. And then at some point, it's going to hit the origin. So it's going to hit the origin here at some point. And then it's going to go backward, go further and go in the negative direction. So it's going to come at some other time. It's going to come over here. So it'll be going to minus A. So let me show some of these tick marks. So there's one tick mark. At some given time, it's going to pass through the equilibrium position. And then it's going to get to this point over here. and then it's going to come back to the origin or equilibrium position, and it's going to come back to the maximum amplitude point. And then it'll keep doing this forever. On a frictionless surface, it's going to keep going back and forth forever. But if I want to plot this motion, the curve is not a straight line. It actually ends up being a sinusoidal function, which is like a cosine curve. I'm not freehand drawing, so you got to give me a little bit of liberty with this. And then, by the way, this will keep continuing. And you guys recognize this curve as a cosine curve. It's very similar to sine curve. The only difference for the sine curve is that the sine curve for time 0 starts at the origin. The cosine will start at 1. So in this case, it's not 1, it's an A. That's the only difference. So the position time graph, it turns out, is a x versus t, as x as a function of t. It ends up being A times cosine of theta. So cosine of some angle. And the reason I do A times is cosine, as you know, is limited between +1 and -1. So by multiplying by A, I end up varying the position between +A and -A, which is what we want. And in this case, the value of theta ends up being, in the terms of our variables, 2 pi over capital T times little t. So the theta is 2 pi over capital T times little t. Let's see if that makes sense and get comfortable with what that is. And by the way, that is the same as saying A times cosine of 2 pi little f times little t, because 1 over t is f from the previous discussion. So this t here is the time at any given point. So this would be the time. Time is just the general x variable. In order to make one full oscillation, the elapsed time between here and here, you guys know this is one full oscillation. So we just defined the period capital T as the time it takes for one full oscillation. So the time it takes from here at 0 to this point, this would be capital T. And so this will be T over 2, and so on. So I got capital T here. And you know that a cosine function goes through one full oscillation for an angle of 2 pi radians, right? So we're doing everything in radians in this part of the class. And so one full oscillation means 2 pi radians. And so when little t equals big T, we want theta to be 2 pi. So that's what gives us that function. So if I generally set theta as 2 pi little t over big T, you can see that when I set little t as big T, the t's cancel and I get theta as 2 pi, which is why this function is defined as this cosine curve. So this function gives us a complete definition of a simple harmonic motion. We will study this a little more in the next video.